Okay, this won't appear on the video, but I wanted to do a little review of last time. Uh, Suppose I have the following. I have a utility function that's made up of two goods, X and Y. Um, So the more of X and Y I consume, the better off I am. But I have a budget constraint where my income is equal to the price of X times X plus the price of Y times Y. What I'd like you guys to do is set up a Lagrangian, like we did last week, with that information. It's okay, you can look at your notes.
Can we look at our neighbor's notes?
Sure. Now, if you remember, Lagrangian is simply a way to optimize our objective function. In this case, our objective function is our utility function with a constraint. A little bit of primero X, luego Y, y luego lambda.
Pero es igual.
Sí, pero este es lambda, ¿verdad? Multiplicado por Y, multiplicado por negativo de X. Entonces, le falta aquí PX.
La derivada del precio
¿Perdón?
que es la derivada del precio de.
Es el derivada parcial a X, entonces como es X multiplicado a X se queda. Okay. Entonces este es multiplicado por la restricción. Es Y menos PXX menos PX. Okay. It's my math person, she has no problem. Okay. So we set up the Lagrangian, right? Equal to our objective function. And then we rewrite our constraint, right? Basically, we can think of it as setting equal to 0, even though we really don't. But it's just like we did, right? It's I minus PXX minus PYY, but we have to multiply it by that Lagrangian multiplier. Lambda, that's what we call the Lagrangian multiplier. I minus PXX minus PYY. So this is our objective function, this is our constraint. Okay. So now, we want to take what we call our first order conditions, which are the partial of my Lagrangian first with respect to X, then with respect to Y, and then with respect to lambda. Now, notice we have three unknowns. We have X, Y, and lambda. I'm assuming we know I, Px, and Py. So first, with respect to X, so I didn't give this a functional form, so I'll just call it the partial of U with respect to X. In the notes, I call it Ux. Right? Plus lambda, negative Px, or Px lambda. That's it. It makes more sense to you guys. And we'll set that equal to 0 because we're going to be maximizing. FOC stands for first order conditions. So this is our first one. I take it the partial with respect to U with respect to X, and then here, right, I doesn't have X in it, so that's the derivative of 0. PYY doesn't have X in it, so that's 0. So what I'm left with is lambda PXX, and I take the derivative of that, I have lambda PX. I do the same thing for Y. I get lambda. Oops. And then finally, with respect to lambda, I just get the constraint. Now that I have this, what I want to do is I want to take those first two first order conditions and solve for X and Y. Now, if you're a math person, you don't have to do it this way. There's three equations, three unknowns. You can do it any way you want. I found that this is the easiest, and I found it's the easiest for students to understand. So I take the first two, and I solve for lambda. So on that first one, right, I take lambda px to the right-hand side, and I get the partial of u with respect to x is equal to lambda px. Then I just divide both sides by px. So here I get partial of u with respect to x is equal to lambda px, which means I do the same thing for my second first order equation, and I get the partial of u with respect to y is equal to lambda. And then I can just set them equal to each other. And this is what we did last week. So that means u, partial of u with respect to x, dx is equal to the partial of u with respect to y, dy. All of that is equal to lambda. And then, as we saw last week, I can rewrite this as the partial of u with respect to x over the partial of u with respect to y is equal to px over py. First I divide both sides by the partial of u with respect to y, and then I multiply both sides by 3x. And this is what I get. And this shows me, as we saw last week, the ratio of my two marginal utilities. That's the partial of u with respect to x, the marginal utility of x, the partial of u with respect to y, marginal utility of y. We call this the marginal rate of substitution, and we see that that's equal to the ratio of prices. I'm sorry?
The other one is the opportunity cost.
It's opportunity cost, right? We move, I'm running out of room. Can I erase over here? And you're right, remember this, the assumption that I'm making when I set those first order conditions equal to 0, aside from I want to maximize, is that I'm staying, right, on that same indifference curve. So, oops. So, that's basically right. The slope of my indifference curve, right, is the ratio of my marginal utilities, the marginal rate of substitution, and of course my budget constraint, the slope is the ratio of prices, x over py, and the intercept is y over px. Okay. So we're going to be doing this, right? But in a non-general sense, and we're going to specify the utility function, and that's what we're going to be doing today. And then from there, from this condition, we're going to move on to other conditions that basically allow us to do other things later on. If you remember, you have a question? Okay. If you remember last week, we assumed that our utility or our difference curves were monotonic. That means as long as we're moving that way, we're better off. In other words, we can't drink too much beer, we can't eat too much ice cream. We don't get worse off. The worst we'll do is be just as well off. Okay. The other thing we did last week is I showed you that I can, from this indifference curve, when I change the price, in this case I have y on the horizontal axis, I vertical. I should have done it differently. I use the FY here, that's it, but nobody. When I change the price, right, I'll see that I get different quantity demanded, in this case of y, and therefore we came up with a demand curve, right? So last week we took that demand curve, and if you remember, I called it a Marshallian demand curve. Marshall was, I think, a 17th century economist, so he gets credit. And it looked something like this, right? We had our indifference curve of the slope. I changed the price, in this case of X, because I have X1 here. And this is a high price, so I get a low amount demanded, a little lower price, a little more is demanded, and a little higher price, a little more is demanded. I connect those dots, and I get a downward sloping demand curve. That's my Marshallian demand curve.
What we say here maybe is you lower the price, your constraint will shift to the right, right? Because you will have more, you will have less constraint.
I don't like the word shift. It rotates, because if it shifted, right, our intercept would change, but our intercept doesn't change, and our intercept doesn't change because in this case, the price of X2 doesn't change, it stays the same. So we get a rotation along the intercept. But you're right, as if when I lower the price, I can buy more of X. I can also buy more of Y because I have more income, which is something we're going to touch on a little later. But anyway, I can buy more of X as the price decreases, and I do. And that gives me my downward sloping demand. Okay. So here it is. If I can do it graphically, I can do it mathematically. And that's what we're going to do. And the first thing we need to do is solve our constraint maximization problem. We'll take our first order conditions. And so before doing that, I want to talk about, we've talked about our utility functions, right? And one of the assumptions I made, or we made, is that those indifference curves are monotonic, like I said. As long as we're moving away from the origin, we're better off, or at least as well off. So instead of writing the utility function in terms of goods consumed, I can rewrite it in terms of prices and income. And that's what that monotonicity gives me. I know that lower prices, I'm better off, and I know with more income, I'm better off, because I can buy more stuff. Now, in truth, my utility comes from consuming, or we assume our utility comes from consuming and not the prices and the income, but rather what I can buy under those situations. But indirectly, those things give me more utility. And that's what we call the indirect utility thing. So we can do this since the amount of goods will depend not only on the consumer direct utility function, but also on the prices of the goods and the income of the consumer. Okay. So the next thing we'll do is derive something known as the expenditure function. How much money do we spend, right? In order to derive the expenditure function, I simply solve for income, I, right, in the indirect utility function in terms of, right, prices and utility, in this case, indirect utility. Notice I'm not calling this U anymore, I'm calling it V. But I can substitute P, since it's monotonic, for my direct utility function U. Right? So we're B, P1 to Pni is my indirect utility function, and of course my direct utility function is a function of all the goods I consume. Questions? Okay. So, this is what we're going to do now. I have a direct utility function, two goods, X and Y. This is known as a Cobb-Douglas utility function. basically there were two economists in the like 1950s. They surveyed firms between their use of labor and input and capital, essentially. And this is what they came up with. The great thing about this type of function, by the way, they didn't come up with utility function, but they came up with a production function. But mathematically, economists like it because it's easy to work with. And that's what we're going to do. You may not think it's easy, but it's easier than any other type of utility function that's going to give us that convex indifference curve.
First question. What is the end result of the indirect utility function? The level of utility, right? So the
Yeah, it's just a number where if a higher level direct utility, right? If this number gives me this number of direct utility and then another situation gives me a little higher, it's going to be the same thing. It's monotonic. It just moves up.
Okay.
But instead of measuring it in X's, we measure it in prices and income.
Okay, so the result will be a number that will be the utility number.
It'll be indirect because it's through prices and income. Okay, so if I have this, and I have a constraint, which just like we did a while ago, I would like you guys to set up a Lagrangian. Not that big a deal, it's coming up on the next slide. But if you guys can do it on your own, now, that puts us a little bit ahead of the game.
It is minus or is plus?
I'm sorry?
It is minus or plus? M or más?
It's the Lagrangian, this
No, the
plus,
constraint.
thank you. Okay, so here it is. First in general form, right? The Lagrangian. By the way, the Lagrangian is usually in that fancy cursive. But the font always changes on me, so I've just given up. Just a big anyway, so here I have U, X, Y, right, in the general form, U, X, Y, plus lambda, our Lagrangian multiplier, times our constraint, I minus PXX minus PYY. I go ahead and I substitute the utility function the Cobb-Douglas utility function, x to the alpha, y to the beta, right? And now I can go ahead and do my first order condition. That first order condition is going to be the Lagrangian with respect to x, right? Now, sorry, the partial of Lagrangian, the partial derivative of Lagrangian with respect to x. So here I'm going to get x alpha minus 1 y to the beta, right? I'm sorry, alpha multiplied by x to the alpha minus 1 power y beta. And then with the constraint, the only place I have x is right here, right? Pxx, so I have lambda px, and then of course x to the 1 minus 1 or 1. And that'll be my first order condition. Go ahead and write it down for y. I do the same thing. I take the partial of my Cobb-Douglas utility function, right? Plus the partial of constraint, which would leave me with lambda py, and I set that equal to 0. Okay. Are you guys having problems with the partial or the concept? I don't see everybody writing this way. Okay. All right. I want to make sure that everybody has the concept of the partial derivative down. And that's why I'm going through the exercise. I'm making sure. Okay. You're looking at the notes by the G. That's okay. That's what the notes are for. Okay. Does everybody understand how to do it? All right. Well. So, they're my 3 first order conditions. Right? First, right, I take the first order condition of my Lagrangian with respect to x, that's the partial derivative. Of Lagrangian with respect to x, I get alpha x, alpha minus 1, y to the beta minus lambda px. That equals 0. Now here, in this first part, right, ypx is just a concept multiplied by what we're doing, so I just say ypx. Over here, right, I take the partial of my Lagrangian with respect to y, I get beta, alpha, x to the alpha, y, beta minus 1. Again, x here is just a constant, minus lambda py. Again, those two are just constants, equals 0. And then finally, I take the partial of my Lagrangian with respect to lambda, and I get I minus p of x, x minus p of y equals 0. So again, I have 3 unknowns and 3 equations. And I can solve the system. Okay. Did I go too fast? I'm sorry, I saw there's people writing. What? Okay. So I get, I solve for lambda in both cases. So here I have alpha x to the alpha minus 1 by beta, right? And I take this to the other side, the negative lambda px, and now I divide both sides by px, and I get alpha x to the alpha minus 1, y to the beta over px equals lambda. I do the same thing for my second first order condition. And I have two equations that equal lambda. I set them equal to each other. And I get lambda is equal to alpha, x alpha the alpha to the alpha minus 1 power, y to the beta power over px, and that's equal to beta, x to the alpha, y to the beta minus 1 over py, right? Now, I can rewrite that. I can multiply both sides. It's the computer. I can multiply both sides by px, right? And divide both sides by beta x alpha y beta to the beta minus 1 power. So I get beta x alpha y to the beta minus 1 power here over this. There's the ratio of prices. And I get the same thing that we got last time. I get the ratio of prices is equal to the ratio of marginal utilities. And of course, I can do a little bit of algebra here because I have x to the alpha minus 1 over x to the alpha. The x to the alpha over x to the alpha, they cancel. That's equal to 1. So I get basically x to a negative 1 power up top. Here I have y to the beta over y to the beta minus 1. The y's to the beta cancel. And here on the bottom, I get y to the negative 1. I have y to the negative 1 on the bottom. I can bring that up to the top and just get y. And here I have x to the negative 1. I take that to the bottom. So I get alpha y divided by beta x. Everybody see how I did the algebra? Please let me know if you don't. I'll go through it on the board. Not that big deal. Are we good? Please don't just say yes.
Sí, lo que pasa es que, por lo menos, hablando, muchas personas aquí no saben lo que es una desviada o una derivada parcial. Entonces, como que verlo de cantazo y brincar mucha álgebra, te estoy siguiendo, pero brincar como que es confuso,
Okay.
pero yo no se atreve a preguntar.
El primer día, cuando hacemos los ejercicios, los derivados y luego los derivados parciales, si sabes hacer un derivado, sabes hacer un derivado parcial. La única diferencia es que las suposiciones que estoy haciendo. Aquí las suposiciones que estoy haciendo, ¿verdad?
Tratar la otra variable como si fuera una constante.
Exacto.
Eso es lo que cambia.
Eso es que cambia.
Sí, pero-
In other words, right, with that first order condition, that first one, I'm treating y and lambda as constants. And of course, px, py, and I are constants throughout. Here, I'm treating x and lambda as constant. And here, basically, I'm treating, excuse me, I'm treating everything except lambda as a constant. Treating both x and y as constant. And this has nothing to do with the partials. This is just algebra. It's a little ugly. So basically, I have this on the bottom. So I can write y beta minus 1, right? If I have this, I can rewrite that as that. And of course, I can rewrite this, just taking the negative sign through, like that. Okay. And, well, let me do it one more. Let's just go through and do what we're doing here. I have y to the beta over y to the beta minus 1, right? I can rewrite that as y to the beta times y negative beta minus 1. And this, of course, I can write as y beta minus 1. Now I have beta here minus beta, those betas cancel. And I get y to the negative 1.
Okay,
Minus
negative 1.
Ooh, thank you, minus, thank you. Okay. That means I just get y. Let that over here. Okay. So I have the same condition I did when we started the class. That's the ratio of prices equals, right, the ratio of marginal utilities or marginal rate of substitution, what we called. So what that means is, right, this first part right here is my marginal utility of x, right, it's alpha x to the alpha minus 1 power y beta. That's my marginal utility of x. Beta x to the alpha, y to the beta minus 1. That's my marginal utility of y. And of course, those ratios, marginal utility of x over the marginal utility of y, marginal utility of x over the marginal utility of y, right, is equal to the marginal rate of substitution. I do the algebra, and I get something a lot simpler. Y alpha times y times beta times x is equal to the ratio of prices. So now I can solve for y in terms of x. I can do this in x in terms of y too. That's where we start. So I do the algebra, right? Ratio of prices. I solve for y, and I get y is equal to beta over alpha, px over y times x. Questions? Okay. So now I have y in terms of x. But I want y in terms of non-random variables. In other words, I want to get rid of that. I'm sorry? Exactly, perfect. I substitute this. We had 3 first order conditions. I've used 2. I can now use the third one. Right? So I just plug in for y into the first order condition. And I said I wanted to get rid of x. What really I'm going to do, first of all, is get rid of y in our constraint. So I plug that into my last first order condition. This is my last first order condition. I minus px x times pyy, right? My first order condition. And I plug in for y. So I get I minus pxx minus py, beta over alpha, px over py. Of course, the py's cancel, time x. And just my first order condition, I set it equal to 0. Right? And now I just solve for x. So here I take I to the other side. I have I is equal to pxx plus py beta over alpha, px over pyx. Right? The py's cancel, and I'm left with pxx plus beta over alpha, pxx. And of course, I have 2 x's, so I can write it as 1 plus beta over alpha, px. That's I. Now I just get I on the right-hand side by dividing by this thing. 1 plus beta over alpha px. And that gives me x equal to I over 1 plus beta over alpha px. This is my Marshallian demand function. This is my demand function for x. Right? Now, it's a function, right? So my demand for x is a function of income and the price of x. An interesting feature of our Cobb-Douglas production function when we do this is that we don't get a complement or a substitute that affects the demand for X. In other words, the price of Y is not in this function.
Okay. Again, the Marshallian demand function for X, notice it doesn't have PY. I could do the same thing now for Y. I have X in terms of all the, excuse me, all our non-random variables. I can just plug that in wherever I want, actually, in any one of my first order conditions, or I could even plug it in to what I have for Y in terms of X, which is the easiest. So if you remember, let me go back. Down here, I had Y, right, was equal to beta alpha px over py x. I just substitute in our Marshallian demand for X right here. So I plug it in, I get Y equals beta over alpha, 1 over py I alpha plus beta over alpha. I do a little bit of algebra, I bring the alpha up top, so I get beta over alpha, 1 minus py alpha plus beta, alpha, this alpha cancels with that alpha. Oh, and I forgot the I. So I get Y, beta, 1 plus beta, 1 over py I, which I can rewrite, right? Bring in the beta down below because I want to get it in the same, basically the same functional form as I have my X in. Now, in general, this isn't necessary, right? We basically, what we do right here, what we did right here, is a Marshallian demand in terms of Y. But we wrote it for X, something like this, so this is why I wanted to redo it and get it like this. So I get I alpha plus beta over beta py, which equals I over 1 plus alpha beta py. If you remember, X was I over 1 plus beta alpha px, right? So now they're similar. Okay. So now I have my Marshallian demand for X and for Y. And that's basically what we did last week graphically, right? We had our points, we changed the price, and we had a demand curve. This is the same process, just mathematically, with the Cobb-Douglas production function.
¿Cómo, profesor?
Dime.
¿Cómo sacaron entender un chiquito mejor la utilidad de que X a la alfa, Y a la beta? ¿Cómo sacaron eso?
Ok. La sacaron, vamos a decir que la sacaron del aire. Este es Cobb-Douglas, ¿verdad? Cobb-Douglas es empíricamente era para una función de producción, no de utilidad. Pero es fácil, es algo fácil, es una función que es fácil a trabajar. It's easy to work with. And it gives us all those functions of our indifference curve that we want. We want that monotonic convex indifference curve. And that's what it gives us. And that's why we work with it. That's why economists love it so much, because it's easier to work with and it has the properties that we think a utility function should have. I don't think anybody out of the 7.5 billion people on this earth actually has a Cobb-Douglas utility function. But it's, like I said, mathematically it's easy to work with, and that's fine.
En el valor original del exponente, ¿verdad? Porque alfa y beta tienen que sumar a 1.
Ok. Si alfa y beta suman a 1, entonces lo que tenemos es
debe sumar a 1.
we have constant returns to scale from X and Y. In other words, what that means is that if I increase X by 10% and I increase Y by 10%, my utility increases by 10%. If they're equal to 1. If they're greater than 1, and I increase both X and Y by 10%, my utility increases by more than 10%. And if they're less than 1, it's the opposite.
En otras palabras, no tienen que sumar a uno.
No tienen que sumar para uno. Ese es un punto, that's something that, again, it makes the math easier when they sum to 1, when alpha and beta sum to 1, but they don't need to sum to 1. And I've given tests not using a Cobb-Douglas production function where all the students assumed that alpha plus beta equals 1 because it was easier. So later on my test, I had to assume alpha plus beta does not equal 1. Okay. So I have y is equal to I plus alpha beta dy, and then I have x is equal to I over 1 plus beta alpha. Yes. And those are our two Marshallian demand functions for x and y. So now, that basically is, like I said, what we did graphically last week. Now what I'd like to do is go ahead and plug these two Marshallian demand functions into our original utility function, right? And what that's going to do is it's going to give us utility in terms of income, I, and our prices, Px, Py, and of course those two constants, those two exponents, beta and alpha. And we're going to call that our indirect utility function, right? Now it's indirect, why? Because x or y is no longer a utility function, only the prices and income. This is our indirect utility function. Questions? Okay. Now, what I want to do is go from this indirect utility function to our expenditure function. In other words, now how do I spend my income? Where do I spend it? And how do the prices affect that? So what that means is I have to do a bunch of ugly algebra to solve for income. So the first thing I do, right, is have all this with respect to alpha, all this with respect to beta, right? And I have I up top, right, which I to the alpha, I to the beta, so I get I to the alpha plus beta, and then I just multiply what's in the denominator. So I get px to the alpha, py to the beta, 1 plus beta over alpha to the alpha, 1 plus alpha over beta to the beta. So I can take this and rewrite it as, well, let me take this first part. Let me explain it, then I'll write it. What I'll take this one and I'll write it as alpha over alpha. And what that'll give me is alpha plus beta over alpha.
And over here, I do the same thing, beta over beta, and that gives me beta plus alpha over beta power.
So let me just go through the step I'm missing. Would that be beta? Beta. And over there, I'm gonna write that as alpha over alpha plus beta over alpha to the alpha. And over here, I'll write the one that's beta over beta plus alpha over beta to the beta. And then I can just rewrite this as px to the alpha, py to the beta. I have alpha in both denominators, so I can write it as alpha plus beta over alpha to the alpha. And over here, I have beta in both denominators, I have beta plus alpha over beta all to the beta. And here I have alpha, oops, I got the numerator. So here I have alpha in the denominator. I'm going to bring it up to the numerator. And here I have beta on the bottom of the denominator, and we'll bring it up to the numerator. And doing that, I get I alpha plus beta, alpha to the alpha, beta to the beta, px to the alpha, py to the beta, alpha plus beta to the alpha plus beta. Okay.
Okay. So now I have I where I can get it to the other side. So basically what I do is I multiply, or I divide both sides by alpha to the alpha, beta to the beta, and I multiply both sides by px to the alpha, py to the beta, alpha plus beta to the alpha plus beta power, right? To get it all to the other side, and I have I to the beta plus, I'm sorry, to the alpha plus beta is equal to px to the alpha, py to the beta, alpha plus beta to the alpha plus beta power over alpha to the alpha power beta to the beta power times d, our indirect utility function. And then, of course, all I have to do is take the exponent to the other side, or the root of that exponent to the other side. So I get all of that to all of this ugly stuff right here to the 1 over, I'm sorry, to the 1 over alpha plus beta power times v to the 1 over alpha plus beta power.
That is my expenditure. It's ugly. The truth is, if we assume our convex utility function, there's no way around it. It's going to be ugly. In fact, in a little while, I'm going to give you another example with a separative utility function, and I promise not to give it to you. And that becomes even uglier. Even though the utility function doesn't seem as ugly, it's actually ugly. Oh.
Okay. So now, basically, I rewrite that expenditure function, do a little bit more algebra to bring everything inside, because I can get rid of the exponents on the alpha plus beta because I have alpha beta to the top. So I get all of this ugly. And then I can substitute in my indirect utility function v for my direct utility function u. And I can do that because they're monotonic transformations of one another. Right? They keep the same order. Questions? Okay.
Okay. So where are we? And this is a legitimate question, it's not a rhetorical question. Where are we in terms of understanding what I just did? I know a lot of times when I sat in your seat, I mean, as a student, a lot of times I didn't understand what the professor was saying at the time, but when I went back and I went back and I studied the stuff, I clicked on.
I think it would be nice to do one with numbers.
Okay, what are we doing with numbers?
Puedes poner el 3 y 4, el simbolito raro.
Letra griega.
¿Cómo se llama?
Letra griega.
Do I have constant do I have constant returns? Do I have constant returns? Do I want alpha plus beta equal 1?
Okay. Easier.
Me imagino que sale bastante fácil, o sea, simplifica un montón el proceso de álgebra, para entenderlo. Si le pone en la letra griega un 3, ponle un 3, x a la 3 más y a la 3, y sale, y sale mucho más fácil. Como que,
Okay.
y no lo el álgebra, la complejidad del álgebra se reduce bastante. ¿Sí? Mi opinión, ahí tú sabes.
Tell you what,
I can do this.
¿De qué?
Nada de exponenciales, porque si se las dan, pues
No, es que tiene un repasito con video y todo, pero ahí dividimos por aquí.
this is your first homework. You guys remember what I told you the first day of class?
iban a tratar de no hacer, dar asignaciones.
I didn't say that, I said, I wasn't no, but thank you for making it, thank you for giving me an out. Pero, this is one with numbers. And I have one here that I assigned the students that has 3 goods instead of 2. And it's a pain and it takes a while. It takes longer because all of a sudden you get 4 first order conditions and 4 equations. Now, if you don't matrix algebra, it makes it a little easier, but you don't need matrix algebra. You just plug and plug and plug and plug until you get the answer, just like we did. I have you do this because, oh wait, and here I have you do the indirect and the expenditure function, and then I give you the numbers, and then I have you do the numbers. And I do the same thing for the 3 variable case. This is just to show you that it works with more than 2 variables. I could do it with 4 variables, 5 variables. It's just the algebra gets crazy, but it's doable. Now, I can leave this for you guys if you guys think that it's better, or I can do this example or another example right now. That's basically what I brought it up.
Sí.
And
El primero, el número 1, es un buen ejercicio para...
I'll do it a little differently to let you guys do this one. If you guys
Vale,
want.
la asignación para...
But la pregunta es, ¿tú quieres que la haga ahora? ¿O prefieres que la haga la semana que viene? O el sábado. La próxima reunión. So you guys can know that you did it right. That's up to you. Would you rather me do it now? Or would you rather do it on your own and then have me check yours?
Yo entiendo porque le va a dar una base para entonces hacer los otros.
Okay. By the way, my computer died. Fortunately, it's the university computer that died, so they gave me a loaner. This thing's really big, but it doesn't have the touch screen. So, let's see.